If you're looking to write cleaner, more maintainable code, there's one acronym you absolutely have to know: SOLID. So today, we're going to break down these 5 fundamental principles of great software design. Let's get into it.
So, have you ever been on a project that started out all nice and clean, but a few months down the line, it's just a tangled mess? You know, where one tiny change over here breaks something completely unrelated over there? It's a super common problem, but thankfully, it's a solved one.
And the solution lies in these 5 guidelines, known by the acronym SOLID. You can think of them as the bedrock of good object-oriented design. They help us build software that doesn't just work today, but is also robust and ready to scale for years to come.
We're going to walk through each letter of SOLID. We'll cover focusing our classes, extending them safely, making sure they behave predictably, keeping our contracts lean, and finally, wiring the whole thing together flexibly. So, let's kick things off with this.
All right, first up is S for the single responsibility principle. And the idea here is actually really simple. Just do one thing and do it well. It's all about giving every single piece of your code one clear purpose.
To make this concrete, imagine a baker. But this baker has to do everything. They bake the bread, they manage the inventory, they order the flour, and they work the cash register. I mean, what's going to happen? Their main job, the thing they're best at, baking amazing bread, is going to start to suffer, right? Their focus is just split in too many directions.
And that brings us to the formal rule for our code. It means a class should have one and only one reason to change. If you need to update your inventory logic, you shouldn't have to even look at the class that's responsible for baking bread. That separation is key.
So on the left, you can see the problem. This one giant baker class that's just a recipe for disaster. But the solution on the right is so much better. We just break it down. Each class has a single, focused purpose. This makes the code way more robust and a whole lot easier to debug.
Okay, so our classes now each have one job. But what happens when we need to add new features? Well, that brings us right to O, the open-closed principle. This is all about adding new functionality without breaking what's already working.
Picture an online store's payment system. It works perfectly for credit cards. It's tested, it's reliable. Now your boss wants to add PayPal. The absolute worst thing you could do is dive into that working credit card code and start messing with it. That's just asking for bugs.
The principle states that your code should be open for extension, but closed for modification. So what does that really mean? It means you should be able to add new functionality without ever changing the existing proven code.
And here's how you do it. You start with a general payment processor concept, or an interface. Your original credit card processor uses it. Now, when you need to add PayPal, you simply create a brand new PayPal payment processor class that also uses that same interface. The original code, never touched. It's beautiful.
So now we can extend our code safely. But how do we make sure those new extensions don't cause bizarre, unexpected problems? That leads us straight to L, the Liskov substitution principle. Now, this one sounds a little academic, I know, but it's really just about making sure our code behaves exactly how we expect it to.
Here's the classic example you always hear about. We all learned in geometry that a square is a type of rectangle. So it's really tempting in our code to make a square class inherit from a rectangle class. But trust me, this can lead to some really weird bugs.
Computer scientist Barbara Liskov put it this way: you have to be able to substitute a child class for its parent class without breaking anything. In short, a child class has to play by the parent's rules. No surprises.
Okay, so look at this. If you have some code that expects a rectangle and you tell it to set the width to 10, you expect the height to stay the same, right? But if you sneak in a square object instead, well, setting the width also has to change the height to keep it a square. That's a totally unexpected side effect. It breaks the contract of the parent class, and that's a Liskov violation.
So Liskov's principle is all about behavior. Now let's talk about the contracts, the interfaces that define that behavior. This brings us to I, the interface segregation principle. Think of it as the single responsibility principle, but for interfaces. Let's go back to our restaurant analogy. Imagine you're a vegetarian. The waiter comes over and hands you one of those giant laminated menus with everything on it: steak, seafood, cocktails, and somewhere in there, a couple of vegetarian options. You're forced to sift through a ton of stuff that's completely irrelevant to you. Wouldn't it be better to just get a smaller, vegetarian-only menu? And that's the core rule right there. Our code, our clients, shouldn't be forced to depend on methods they don't use.
It is so much better to have many small, specific interfaces than one big, clunky, general-purpose one.
So instead of one fat interface, we just segregate it. We split it up into smaller, more specific ones. A juice bar class only needs to know about the drink menu. It doesn't care about the food. This whole approach keeps our system clean and makes sure our classes aren't burdened with things they just don't need.
We've covered how our classes and interfaces should be designed. Now for the final piece of the puzzle. D, the dependency inversion principle. This is a big picture rule that ties everything together. It's all about how the different parts of your system should connect to each other. Think about how we, as developers, use something like Git. We depend on the idea of version control, committing, pushing, pulling. We don't really care about the super specific nitty-gritty implementation details of how Git works under the hood. That abstraction lets us work at a higher level without getting bogged down.
And the formal rule reflects that. It says our high-level modules like our core business logic should not depend on low-level details, like a specific database or file system. Instead, both of them should depend on an abstraction, like an interface. That interface acts as a buffer, decoupling the two, and that makes your system incredibly flexible.
So after all that, why does this really matter? Well, it makes your code way easier to maintain because changes are isolated, it supports growth, letting you add new features without being terrified of breaking everything, and it gives you incredible flexibility, letting you swap out details like a database without having to rewrite your core logic. Ultimately, it's about building quality software that lasts. So as we wrap this up, I want you to think about the code you're working on right now. Which one of these principles could you apply, even in a small way, to make it just a little bit cleaner and more robust? You don't have to do them all at once. Just start with one. That small change today can make a huge difference tomorrow. Thanks for tuning in.